This problem's from the 2015 AP Stats exam. It's FRQ number 3 from that year. It's a probability question, so it's rooted in Unit 4 of the course and exam description. So in this problem, they tell us that a shopping mall has 3 ATM machines. The machines receive heavy use, so sometimes they're going to stop working and need repairs. We're going to let random variable capital X represent the number of ATMs that are working when the mall opens on a randomly selected day. The table shows the probability distribution of X. So we either have 0, 1, 2, or 3 ATMs operational when the mall opens. The probability of each of those numbers of ATMs working when the mall opens is given in that bottom row. Part A is asking us to find the probability that at least one ATM is working when the mall opens. So I didn't really have to do this, right? Capital X is the number of ATMs working when the mall opens. That's already done back here. Certain probabilities aren't going to do that, so I think it's just a good habit to get into to make sure that you are consistently naming your random variable, even though it was already done for us in this case. And the question is, what's the probability that at least one ATM is working when the mall opens? Well, that's the probability that X is greater than or equal to 1. So that's the probability that X is equal to 1, or X is equal to 2, or X is equal to 3. This is a situation where the events are mutually exclusive. I can't have both 1 and 2 ATMs operational during the time frame when the mall opens. It's either going to be 1 or 2, but not both. So all I'm needing to do is add together the individual probabilities of each of these outcomes. X equals 1, X equals 2, X equals 3. When you do that, you get 0.85. This secondary calculation here does not have to be shown. You'd want to go one way or the other. This will work. It's actually a little quicker to get to the conclusion with this version of the calculation in this particular context. What's the probability that X is greater than or equal to 1? Well, the only time X is not greater than or equal to 1 is if X is equal to 0. That has a probability of 0.15. So if I use a complementary calculation here, I can get that same answer a different way. You'd want to show one of these or the other. I've got a little piece of the scoring guidelines copy and pasted here. You got to essentially correct with this part if you had the right probability computed and the work shown. One thing that I would be a little concerned by would be if you concluded part A by saying 85%. They're specifically asking for a probability, and in statistics, a probability is defined to be a value between 0 and 1. So make sure you give that answer between 0 and 1, 0.85 rather than 85%. Part B is asking us to find the expected value of the number of ATMs that are working when the mall opens. Now, most of the time in AP Stats, you're going to be able to find the formula that you need to do certain calculation off of the formula page. That's actually not the case for expected value. The way that you're going to find the expected value of a random variable or the mean of a random variable is you're going to take the, in this case, number of machines that would be operational when the mall opens times the probability of that amount being operational plus the next potential number of machines operational when the mall opens times the probability of that number working, and you carry that calculation forward across each of the remaining columns within the table. And when you do that computation here, you end up with 1.73 ATMs on average will be operational when the mall opens. Now that is a long run calculation. They don't ask you to do this here. So if you go back and glance, every once in a while they're going to ask you to not only compute something, but interpret it. It's just a computation in this particular version of the problem. If they did ask you to interpret the meaning of this within context, you'd want to say something along the lines of, over the course of many days when the mall opens, we would expect that on average, we would have 1.73 machines operational at that time. If you look at the scoring guidelines here, what I just said is not required. You wanted to have the expected value computed correctly with the work shown. So can you keep track of even the calculation back here? Could you have done the calculation in part A, like straight on the calculator and just reported this answer? Done this calculation straight in the calculator and just reported this answer? Sure, but a lot of these probability questions are going to ask you to show your work. So taking an extra 30 seconds to write out the calculation you're computing with the calculator definitely is going to be well worth your while. Part C asks us to find the probability that all 3 ATMs are working when the mall opens, given at least one of the ATMs is working. So this is a conditional probability calculation. This right here is copy and pasted from the formula page. So the probability of A, given that B has already occurred, is going to be the probability of A and B occurring simultaneously divided by the probability of event B. So if we wanted to kind of put this into context for part C, we're asked to find the probability that all three ATMs are working. So what is the probability that X is equal to 3, given at least one ATM is operational, given X is greater than or equal to 1. So we're going to find the probability that X is equal to 3 divided by the probability that X is greater than or equal to 1. Now the probability that X is equal to 3 is pretty simple. That's going to be this 0.24 from the table. The probability that X is greater than or equal to 1, we computed that back in part A. That's that 0.85 answer from back in part A. All I'm going to need to do here is take 0.24 divided by 0.85. That gives you approximately 0.282. So that would be the extent of the work that you would need to show for part C. If you look at the scoring guidelines, we have the probability computed correctly. The work is shown. I copy and pasted a little bit of the partially correct portion here because, again, I would think that when you write this out, you kind of know what you need to do, but you have to show the grader that you knew which number went in place of this and which number went in place of this. And showing this extra line here, which, again, does not take that much time to do, is definitely going to be well worth your time. Haven't had this happen yet within this problem. We're basing this calculation here off a previous answer. Even if you were convinced your probability back here in part A was wrong, and hopefully this is an easy enough calculation, you don't think that it is, but just in general on the AP Stats exam, you would want to base your calculation in part C. If you recognize that it depends off your calculation from an earlier part, you'd want to base it off of that same thing, even if that answer earlier on was wrong. Still receive full credit if you maybe got an answer of 0.8 back in part A by some weird chance. If you had in part C 0.24 divided by 0.8, this number is not going to be the correct number if you had 0.8 here rather than 0.85, but you would get essentially correct in part C. So when you're in a spot on the AP Stats exam where new answers depend on previously determined answers, make sure you stay consistent and use that previously determined answer, even if you're fairly certain it might be wrong. Last part of this says that given at least one ATM is working when the mall opens, so this is kind of a continuation of what we were dealing with back in part C, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the number expected from part B? Explain. Now, here's what occurred to me when I read this. I just did part C and I got an answer of 0.283 for the probability that 3 ATMs are working if at least one is operational, or given that at least one is operational. That increases from a probability of 0.24 that we had in the original table. If this column is not a possibility because we know that at least one ATM is operational, we're going to have our expected value increase, because if we did a calculation similar to part C for the probability that one ATM is operational given at least one is working, or the probability 2 are operational given at least one is working, these values are going to also increase slightly from the original table because this is eliminated as a potential possibility given that at least one is working. Our expected value is definitely going to increase because of that. So I've got all that kind of mentioned here. If you would actually build the new probability distribution table, right, eliminate 0 as a possibility and do a calculation like you did in part C to adjust this 0.21 upward a little bit, do another one similar to what we did in part C to adjust this 0.4 up a little bit, we already know what this is going to adjust up to. But if you actually compute the new expected value, that would be another way to do this without having to really get into the wording here. Now, when you are explaining something, make sure you are explaining it within context and that you are not being generic and just saying it will go up. Make sure you're giving reasons why, make sure you're including the context of the situation. Last little glance at some scoring guidelines here. There's a little bit of flexibility in what you do. So I think what I did, if you read that paragraph on the last screen, is pretty much what this first explanation is. If you look at this last one, I kind of explained that, right? If you actually compute the new expected value from a new probability distribution table, that would get full credit as well.